Hello, good afternoon to all.
Good afternoon.
I'm Ashok Vidate. Today I will deliver a lecture on the counters. So in that counter is a device which stores the number of times a particular event or a process has occurred, often in relationship to a clock signal. There are two types of the counters or which counts. So we are calling this one as counter. The counters are mainly the two types, up counter and the down counter. So in that up counter, each of the higher order flip-flops or here the counting is performed in the high output side or in the increment side, and in the down counter the counting is performed from the high value to the low value. So in that lecture we will find out the code for the 4-bit up counter. So in that 4-bit up counter means here it starts increasing its value up to the 4 bits or 0000. These are the 4 bits. Up to that 4 bits, the counting has been started. So the flow chart for this counter is nothing but the start, then initialize entity, then here increment or if clear, or at the starting point we are clearing all this data or data must be at 0, then we are increasing the enable clock, or generally we are using for the counting the clocks, we are using the counter, and value is increased from 0 to 15, because if it is a 4-bit, that is 0 to 16 bits we have to calculate and end. So the VSDL code for this counter, firstly we are declaring the IEEE, that is the library. So library declaration we are using the IEEE logic. So we are use IEEE dot std underscore logic, or that logic we are using, as well as unsigned operation. We are increasing in the positive form, so there is no any negative signs required. So yeah, unsigned operators we are using. The next point is that define the entity, or the entity defined is as a counter, or entity of the counter is. So in that entity we are defining the clock, then here clear. These are the inputs, or clock and clear. These two are the inputs and Q is the output, that is the out STD logic number, that is 3 down to 0. And here end of this counter or end of this entity model we have described. So after that, the architecture we have to define. The architecture of counter, or the architecture name is architecture of the counter is signal. So here we are using the temporary signal whose value is changing. That is the uh, standard underscore logic, or this logic are nothing but the 3 down to 0. Then begin. So we are starting the process of this counting. So the process we are starting the counting, or in that process the values we are counting are nothing but the clock, and at the starting or beginning we are clearing all the data. So for that purpose clear signal we are using. So begin, if clear is equal to 1, then temporary assigns the value 000. If there is a clear all these values, then here first value is 000, and next time we are increasing that values, or if that clear is not present, then else if clock event or here clock is equal to 1. So when we gives clock signal high to that clear terminal, at a time it goes to the reset condition, or here all data is clear. So the, for that firstly we are counting with respect to clock, that value is 000 for clock 1. Then for next clock 0001. For third clock 000. Then 0010, like that, or 11. In that way we are incrementing. For that purpose we are using the temporary signal. The temporary is related with respect to temporary signal is standard vector logic signal, or that is related with the clock, and we are increasing as per the clock's increases here the counting starts to be increasing, and that increased value are assigned at a Q point, or that is Q is nothing but the output, and clock and reset, these two are the input and end of this architecture. So in a simple way, we can demonstrate by that clock signal, or here the 4-bit signals we are using. So after the every clock, if their clock is increased, or clock is 1 at a time, here it is a 0, then 1, then 2, then 3. First clock, that is 000, second clock 001, then third, then fourth, and like that. In that way, these are blocks are increasing forward. So in the similar manner, we are able to perform this operation for the down counter, or in the down counter we are starting from the higher level values towards the lower values, or if there is a, we are saying that we want to show that ending time for that purpose we are using the down counters, or in the down counters first we start initialize the entity. After that, if clear is equal to 1 on, then enable clock, then counter value decreases from 15 to 0 in the opposite side. So in that library declaration is same, entity declaration is also same. So only the process we are defining in that architecture. So in that process, how we are able to define it. So firstly, if that clear is equal to 1, then temporary value is assigned as 000. Else clock tick event and clock is equal to 1, then temporary value is assigned temp plus 1 and end it. And end process. Where Q is assigned by the temperature and end architecture. So this one is for the counters. The next one is nothing but the shifter register. Shift register, in that the register values are shifted from one side to another side, or next points or next bit data. We are shifting that value for 1010 values. We are shifting with respect to the input clock. So clear is also terminal is available and clock is also available. Based on that, Q0, Q0, Q1, Q1, or here Q2 and Q3. After that next cycle, these are shifted. So for that purpose, we are using the shift register. Or here, the shift registers can be categorized into serial input, serial output, as well as serial input, parallel input, parallel output, or parallel input, serial output. Then 4 ways we are able to define the shift register. So firstly, we will study about the parallel in, parallel out shift register. Or in the parallel in shift register, the data is parallelly inputted. Here, the input are given in the parallel form, but at the output side, we are also obtaining the data in the parallel forms here. At the same time, all these values are present. At the same time, all these values are given as an input. So we can call this one as a parallel register. Or all the bits appear on the parallel outputs immediately following the simultaneous entry of the data bits. Following circuit is a 4-bit parallel output register constructed by the deep flip-flop. Or here, that is the deep flip-flop we are using to construct that parallel register. So the D flip-flops are parallel inputs and Q are the parallel outputs. Once the register is clocked, all the data and the D input appear at the corresponding output. Because in the D flip-flop, each value is present at the input side when clock is high, that value appears in the output side. So here, if there is 1, at that time the output value is also 1. If there is 0, output value is also 0. So that value is present after the clock. So to design that parallel out shift register, we are using the IEEE library declaration, then entity. The entity name is PIP, parallel input, parallel output is port here in STD logic, that is the clock is also in STD logic, then D. These are the D is nothing but the input or vector D input 3 down to 4. There is a 0, D0, D1, D2, D3 or 3 down to 0 like that. Then Q is also same output, that is the Q0 to the Q3. Then we are clock and reset. These are the one times signals are available. So only Q and D, these are the three down to 0 signals. Other signals are single signals. Then architecture of this parallel out can given as process. And here in that process we are considering the clock. Begin if clock tick event and clock is equal to 1, then Q is assigned to value of the D and ending. Here that is in the vector form. So here Q0, Q1, Q2. That value is assigned to that Q value and in architecture. So it is a very simple to define that shift register architecture or parallel out architecture in VHDL form. Similarly, serially parallel shift register or in that serially parallel shift register, all data bits appears on the parallel output. Output is in the parallel form, but we are giving the input in the serial or bits are entered sequential, means one after another the bits are entered, but at the output side all the bits available at the same time. So for that purpose, we are using the deep flip-flop, or in that how we are represent. Or serially, we are input or giving the data as an input. So here entity or IEEE library definition is same. Then entity serially parallel is clock clear. These are the same data input. That is the Q is the 3 down to 0. Then how can that process? If clear is equal to 1, then Q assigns the value 0, 0, 0, 0. If clock tick event is equal to 1, then 3 down to 0. Q assigns the value 3 down to 0 means here the representation is given or here input is given into the serial inside. So here Q 2 down to 0 and here Q 0. So here in that serial or input is provided in a sequential form or in the serial form one after the another. So these are about the VHDL codes for the shift registers. Then we will study the VHDL code for the static line, the shift register. For this 8-bit shift register, how can we study that 8-bit shift register? If we are asked for the 8-bit shift register, we are going to write down the code as it is. Following is the VHDL code for that 8-bit shift register of the left shift or the right shift. So in that IEEE library declaration, the entity code. So here, port are nothing but the C stands for the clock, SI stands for the serial in, SO stands for the serial out logic. Then end shift register. So entity declaration is ended. Then the next one is architecture declaration. The architecture declaration of the shift register, we are using the signals. The temporary signals are nothing the standard logic vector. Or in the previous one, we are considering the 3 down to 0 in that one as it is the 8-bit. We are considering as a 7 down to 0 and begin. Then process C. Begin if C, that is the C tick event and C is equal to 1, then for I in the 0 to 6 loop, temporary value is assigned as a temporary plus 1. Here that value is incremented by 1. and that incremented by one value is a previous value of the signal. So end loop, end temperature 0, SI and end. And that has been continued up to the temperature signal 7 is assigned to the S0. So this one is the 8-bit code for the shifter register or 8-bit shifter register. Then we will study about the HDL code for the static RAM. So here VHDL memory models, or in that VHDL memory models for the ROM. ROM is the volatile memory. Or here read only memory. Not as volatile, it is a permanent memory. What we have stored into that ROM that does not erase. So that is the read only. After that return, it is only we are able to read, not able to write. So that we are calling this as a read-only memory. Similarly, the RAM stands for the read and write memory. The RAM stands for the read and write memory. So firstly, we study about that static RAM. Or RAM stores data or temporary data has been stored into the RAM and permanent data has been stored into the ROM. So here the simple model for this memory has been given as library declaration firstly, then entity or entity we are using the RAM. That name of that RAM is 6116. So that 6116 that RAM we are storing the data. So here for the storage purpose we are using the address lines or which location we have to store that data. So for that purpose the port are the in or out. Or in that port the address bits are nothing but in unsigned 7 down to 0 for this 8-bit storage. 7 down to 0 that's the in bit, then data bits are nothing but the in out or data can be stored or input as well as data can be recovered. We can able to say that we are able to store the data as a particular location. So we are for the storing, we are calling this one as in operation and to read that data from the particular location, we are calling this one as the out operation. So here data in out standard logic vector that is the 7 down to 0. Then the signals which we are using for the write is nothing but the write enable underscore B, write enable bit, then control signal bit, then output enable bit. Here route enable we are able to, when that bit is high, at the time we are able to write. When control enable, we are able to control that memory, or here to erase that memory, we are using the control C. Then to obtain the output or the data which is stored, for that purpose we are using the output enable and in std logic. Then E&TC, that is the RAM 6116. A simple memory model for that RAM. In that architecture, we are defining a simple RAM of RAM 6116 is. The RAM type is an array from 0 to 8 minus 1 of the standard logic number 7 down to 0. Signal RAM, RAM type, others will begin and process. So data is assigned the value of a chip. If that chip is not selected, then if that chip is selected or that name is selected RAM 6116, then here the program starts as a big control signal assigns to value 0, then the control signal is low level, then with rising edge, starting 0 level and rising edge, you can call this one as the right enable, then this operation is the right operation. At this time, the writing the RAM1 convolution integer address. For here, the address can be given by the operator who want to store, and after that address, the data we are assigning to that value, that address. And after that storing, we are waiting for the 0 and 2nd in it. We are doing, there is no waiting, we are performing. The next one, if there is a write enable bit is 1 and output enable bit is 0, then the operation is nothing but the read operation. So in that read operation, we are recovering the data or finding the data from the address location. So here we have that address assigns the value of RAM convolution integer address, or that address locations value has been assigned to the data. Else, data assigns the value of others or no value, and edit. Then edit, then wait on the right enable bit, then control signal bit, then output enable bit and addresses. For that purpose, wait and end process in simple array. That is for the event. So that behavior code is for the RAM 1, but we have to say about that ROM, or here dynamic RAM. The dynamic RAM, the values are changed dynamically, or internal side, the values gets changed as per the input given in that RAM. So we are calling this one as a dynamic RAM. This is also same 7 down to 0 RAM, or here 8-bit RAM. So how we are able to define the behavior of that dynamic RAM? So to define the entity and library declaration are the same, only the architectural declaration is different. Here the entity declaration is same as per the previous one. The only the architecture, or in that architecture we are actually describing how that model can work. So architecture behavior of DRAM 1024 is, so we are begin with the process P0 process, that is the RAS, that is the read enable signal, control enable signal, and then write enable. Is then D type with that bracket, we are defining the signals which are input to the RAM, or which are variables, or the signals which are varying with respect to time. So the type, the DRAM array is array from 0 to 2 is to 10 minus 1 is here 2 to 9 of standard geologic vector, that is the 7 down to 0. Then variable row address integer RAM range is 0 to 5 minus 1. Then variable memory address integer range from 0 to 2 minus 1. The variable DRAM array. So in that variable define the general form of this array. We are calling this as D array. VSDL code for raw. So that one is the VSDL code for the raw. So in that library declaration is same entity declaration, or in that entity we are giving the ROM as the name of the ROM signal. The entity name is the port address, the yesterday logic, that is vector we want to the data out yesterday vector, that is another 7,000. The architectural behavior of the ROM signal is the ROM type is an array that is from 0 to 7 of the standard logical 7 dimension. The signal ROM or the version's value are as per like or not. These values are the 1111 0 11 0 1 0 0. These are the up particles set. In that one, we begin when data out or data we are in the ROM, we are only performing the reading operation, not as a writing operation. So we read out the signal we are listening, reading data out. When there is no impact of the data in, and the out data is available. So that data is ROM convolution integer address. These are the data in and in. So this one is one of the so after that raw and RAM description unit setup and conclusion. So the next one will start with the introduction to the Verilog HDL. So here in the previous one we are using the hardware description language, that is the VSDL. The similar way is nothing but the description Verilog. So firstly, we will study about the unit 3, introduction to Verilog. Okay. Verilog is also hardware description language, and that standard is defined by the IEEE. And in that IEEE, the standard is defined as a IEEE 1364 or standardized as a 1364 is also hardware description language and used to model electronic systems. It is the most commonly used in the design. Okay, can you hear me? Am I audible? Hello, am I audible? Okay, so in that Verilog is a standardized as a IEEE 1364 is also hardware description language and used to model electronic systems. And it is the most commonly used in the design and verification of the digital circuits at the register transfer level of the abstraction. Or register transfer means we are modeling or we are breaking that circuit into the register level, register transfer level, or here RTL level of the abstraction. Or in that register transfer level, the resistors and transistors are available. It is also used in a verification of the analog circuits and mixed analog circuits, as well as in the design of genetic circuits. In 2009, the Verilog standard, that is the IEEE 1364 2005, was merged into the System Verilog standard and creating the 1800-2009. Previously, 2005 standard is present. After that, 2009 standard is presented or it is available for the writing the circuits into the VHDL form. So the overview of that Verilog is it is the hardware description language similar to the programming language because they include the ways of describing the propagation time and signal strength sensitivity. There are two types of the assignment operators. Here, for assigning purpose, two types of the assignment operators are present. Firstly, blocking assignment that is equal to and a non-blocking assignment. Non-blocking assignment. The non-blocking assignment allows designers to describe a state machine update without needing to declare and use of temporary storage variables. Since these concepts are part of the Verilog's language semantics, designers could quickly write descriptions on large circuits in a relatively compact and non-cosine form. At the time of Verilog's introduction, okay, Verilog is introduced in 1984. Verilog represented a tremendous productivity improvement for the circuit designers who were already using graphical semantic capture software and especially written software programs to document and simulate electronic circuits. The designers of Verilog wanted a language with a syntax similar to the C programming language, which was already widely used in engineering software development. Like C, Verilog is also case sensitive. The VHDL language is not related with the case sensitive, but this Verilog language is case sensitive and has a basic processor or through less sophisticated than that of the ANSI or C++ language. Its control flow keywords, that is if, else, for, while, case, etc. are equivalent, and its operator is also equivalent with respect to C language. Or the systematic difference include required bit widths for the variable declaration. Then the Verilog uses begin and end instead of curly brackets. Or instead of using that curly brackets, we are using the begin and end. And many other minor differences. Verilog requires that variables be given a definite size. In C, these sizes are assumed for the type of the variable. For instance, the integer type may be 8 bits, or here 0 to 7 bits we are describing. So in that Verilog design consists of the hierarchy of models. Hierarchy means here step-by-step sequence, or step-by-step sequence, or in the previous one VHDL there is also step-by-step sequence of available. The first step we are declaring is nothing but the IEEE library declaration. Secondly, entity declaration, and lastly, architecture declaration. In the same way, the Verilog design consists of the architecture or here hierarchy modules. These modules encapsulates design hierarchy and communicate with other modules through a set of declared input-output and bidirectional ports. Or internally, a module can contain the concurrent and sequential segment blocks, and instead of the other modules, the sequential statements are placed inside a begin and end block. Or in that sequential statement, we are inserted inside the begin and end block and executed in a sequential order with the block. However, the blocks themselves are executed concurrently, making Verilog a data flow language. So a subset of the statements in a Verilog language are synthesizable, or synthesis. We are differentiating the networks into smaller parts, or we are breaking them into a smaller part for the purpose of synthesis. And in that synthesis process, the register transfer level synthesis can be used. So that synthesis software automatically transforms the Verilog source into a netlist, logically equivalent description consisting of logic, elementary logic primitives. That is, the elementary logic primitives or gates are nothing but the AND gate, OR gate, NOT gate, flip flops, etc. that are available in a specific FPGA or the VLSI technology. The further manipulations to the netlist ultimately lead to a circuit fabrication or the blueprint. After that circuit fabrication, we are able to use that circuit. So that Verilog was created by Prabhu Goyal and Phil Murphy and Chi Lai Hun, or in between 1983 and 1984. So these are invented by Prabhu Goyal, Phil Murphy and Chi Lai Hun and Douglas Warner in between the 1983 and 1984. So the next version of this one is the Verilog 95 and Verilog 2001 and 2005, or here updated versions. So in that Verilog 95, or with increase in the success of this VHDL at the time, the Cadence decided to make a language available for the open standardization. The Cadence transferred Verilog into a public domain under the Open Verilog International, or known as the ASREO organization. The Verilog matter was submitted to the IEEE and became IEEE standard 1364 1995, or the company is referred as a Verilog 95. But after this 95 year, the version has been enhanced in the 2001. So these extensions becomes the IEEE standard 2001, or we are calling as a Verilog 2001. Or here it is a significant upgraded language from the Verilog 95. First, it adds explicit support for tools complement, signed the nets, and the variables. Previously, the code authors has performed signed operations within the above bit level manipulation, or here carry out, carry in. From that manipulation, they are performing the operations. But here, the Verilog is in that Verilog 2001, the operations can be becomes in a simple form, or simply we are able to find out the results. So here Verilog 2001 is the version of the Verilog supported by the majority of the commercial EDA software packages. Then the next language is nothing but the Verilog 2005, or the Verilog 2005 is called as the system Verilog, and that is the IEEE standard 1364 2005, and consists of the major corrections, specific clarifications, and such a few new language features such as unwired keyword. A separate part of this Verilog standard, that Verilog AMS, attempts to integrate the analog and mixed model or mixing a signal modeling with a traditional Verilog. On that Verilog 2005, we are calling this as a system Verilog. So in that previous one, or example by using that Verilog, the for the two flip-flops, or the two flip-flops, how we are able to define. So in the previous one, in that HDL, we are using the library declaration, entity declaration, then architecture declaration. It is a Verilog is a C type language or embedded C language. So in that directly we are defining the module, that is the top level clock, reset, these are the inputs, clock and reset are the input, and register, which we are using as a flip-flop 1, flip-flop 2. Then always add post-age reset or post-age clock. If reset, then flip-flop 1 is assigned value of 0, flip-flop 2 is assigned value of 1, and else. Begin, flip-flop 2 is assigned value of flip-flop 1 is assigned value of flip-flop 2, and 2 assigned value of 1, and end value. In that way, we are able to define or begin and end. Begin and end. Then we start that model, end of this model. That is the model. From this model to this model. Ending. So these are the simple examples of this variable model. So from this point, we will stop here. Then in the next lecture, we will conduct the various examples of those Verilog modules, and the types of these Verilog models, data types, operators, and here hardware HDL implementation of by using the Verilog language. So that part we will conduct we will cover in the next lecture. So